we talked about in my second talk this idea that Newton gave us a couple of rules, a couple of very simple rules that you guys learn in 9th grade physics class if you've been here, and whatever physics class you've been in. You know, objects at rest remain at rest, and F equals ma, and every action has an equal and opposite reaction. And with a handful, 4 or 5 of these rules, basically sets up a system that allows unprecedented prediction of what things in the universe are going to do. And what Newton's laws allow us to do is to plot a trajectory of an object, the moon around the earth around the sun, a baseball that you throw from the outfield to the shortstop, with exact precision. As long as Bill said, you do it one object at a time. And the trick of Newtonian determinism is it's easy, if you've got 1 or 2 objects interacting with one another, to predict exactly what they're going to do based on a few simple rules. This idea that if we know what everything's doing now, we can determine what it's going to do next, sort of reaches its pinnacle and simultaneously starts to decline with Laplace, who we talked about at the end of, maybe the beginning of the 3rd lecture I gave to you guys, where Laplace, in the beginning of the 1800s, 1812, publishes a book called Analytic Theory of Probability. But one of the first things he says when setting up the book talks about this idea of determinism. I didn't bring my French translation with me, but what Laplace says is that basically we can consider the past, well, we can consider the present to be the result of the past and the cause of the future. And if we can imagine some being that could hold in its mind all the locations and all the motions of everything in the universe, and knew the forces of electrical attraction and gravitational attraction for everything in the universe, that nothing about the future would be uncertain to it. It would be able to predict exactly what was going to happen. So if I knew exactly where all the atoms and molecules were in your brain at this moment, and exactly what input those atoms and molecules were going to receive from light waves and sound waves banging against your head, I would be able to predict what you're going to do when you walk out of this classroom, what you're going to say to the person next to you, what you're going to choose from the lunch line today. Because all that exists in the universe is atoms and molecules bouncing off of one another. If they follow predictable rules, we can predict what they're going to do. At the same time, in his theory of probabilities, Laplace recognizes one important fact, which is in practice, doing this is absolutely impossible. We are not a godlike infinite being that can record all the locations of all the atoms in this room. And I talked about the fact that even something so simple as describing the gas in a balloon, if you wanted to know what's a balloon going to do when I heat it up, how much is it going to expand? And you tried to do that by applying Newton's laws to every single atom and molecule in the balloon, what would you have to do? Well, first you'd have to write down all their locations. Where's molecule 1? Where's molecule 2? Where's molecule 3? How many molecules are there in a balloon, a sort of party-sized 12-inch sphere of gas? About 5 times 10 to the 22. That's 5 with 22 zeros. 50 million trillion, billion trillion. I left out and it was 1,000 off. 50 billion trillion atoms and molecules. How would I write down that data? Suppose I put it on a hard drive, right? How much data would that take? Well, it would take 50 billion trillion bits of data just to write down their locations. Actually, times 3, because you need an X, Y, and Z. So 150 billion trillion bits of data. How much storage is that? Well, think about a terabyte hard drive. You can go to Staples right now. You can drive down to Bridgehampton to Staples, buy a terabyte hard drive, probably a 2 terabyte hard drive for about $100, right? It holds 2 trillion bits of information, give or take. So 50 billion trillion molecules would require about 10 terabyte hard drives for every human being in the planet just to write down the locations of all the molecules in a single party balloon. Okay? So if we say, all right, well now let's predict what all those atoms and molecules are going to do, forget about it. It would require a computer the size of the solar system to calculate the effect that molecule 2,150,301 has on the effect of molecule 5,800,462. Okay? And then you'd have to do that with every pair of molecules. It's simply impossible to apply Newton's laws to billions of atoms and molecules to figure out what the air flowing over the wing of an airplane will do, for example. Okay? In fact, it's pretty hard to do it with 3 objects. Forget about a billion trillion objects. So what do? What Laplace recognized is that we can apply the rules of probability, or let's not say the rules, we can apply the methods of probability to a question like this. Just like when you roll 2 dice, you have no way of knowing whether they're going to come up as a 2 or a 7. You do know that if you do it a bunch of times, you're going to get more 2s than 7s. Okay? And if you do it a billion trillion times, you know you're going to get about 3 times as many 7s as you do 2s. And we talked about this last time, that probability doesn't allow us to predict exactly what's going to happen in any case, but it does allow us to predict what a large number of things will do on average. And this idea of probability that Laplace puts forward and starts to try to outline the rules of in analytic theory of probability in 1814, grows into, by the end of the 1800s, through the work of Boltzmann and Maxwell, into something called statistical mechanics. So when we talk about a balloon, we don't talk about what molecule 30 trillion, 80 billion, 200 million, 462,312 is doing. We talk about what the atoms and molecules are doing on average. Most of them are going this speed, some of them are going faster, some of them are going slower. On average, most of the time, they're behaving in a similar sort of way. So statistical mechanics actually lets us make predictions about what the temperature in a room will be if we turn up the heat. It lets us make predictions about how much a balloon will expand if we heat it up and the volume of the gas increases because the atoms and molecules are hitting against each other harder. But it doesn't allow us to say exactly what any one atom or molecule is doing. So it's a different approach to physics that happens by the end of the 1800s, which is letting go of a little bit of certainty, the certainty of exactly where every atom and molecule is, and dealing with probability. And this actually is magnified again in the early 20th century with quantum mechanics, but we don't have time to get into that today. So what we're faced with in dealing with these systems with lots and lots of things interacting is complexity. A much greater deal of complexity than looking at the moon going around the Earth or a baseball that you throw across the room. Complexity can come from 2 different places. One, it can come when you have lots and lots and lots of things interacting with one another. Like the top picture, predicting what happens when one billiard ball hits another billiard ball is fairly straightforward. It's a typical AP physics problem. This ball hits this ball at a certain velocity. How fast will this ball go flying off? It's easy physics. But if you look at the break in a billiards game, where the cue ball hits the 15 racked up triangles of balls and they go flying all over the billiards table, that's very, very difficult to predict. And no 2 breaks are the same. And you never see a pool player call a break the way they call a single ball in the middle of the game, right? They'll say, all right, the 9 ball in the corner pocket, and they intentionally make the 9 ball in the corner pocket. Nobody at the break goes, all right, the 12 ball in the side pocket, because there's no way to predict where that 12 ball is going to go. It's just too complicated. Okay? Another place to get complexity is with non-linearity, and we talked about this in my last lecture, that there are some systems that don't obey the kind of simple Newton's law equations where you double the amount of force and you double the height that the ball travels. There's some equations where if you double one quantity in the equation, the rest of the equation goes completely haywire and gives you completely different behavior. And non-linearity is another source of complexity that we talked about last time. And what this gives us is a new sort of set of systems that we have to deal with, and that's chaotic systems. If you look at a chaotic system, a system that obeys nonlinear equations, like, for example, the equations that govern the motion of air or the motion of fluids, they're called the Navier-Stokes equations. They're nonlinear. If you change something a little bit in one of the variables, all the other variables respond in a disproportionately larger reaction. So you can have a very small effect on a rising column of smoke that is behaving itself in a sort of static fashion, and that column of smoke starts to behave in a more chaotic or turbulent fashion. And this transition from static behavior to turbulent behavior is one that scientists would like to understand. It's important when you're building a car or building an airplane or studying how the water flows through the pipes in your sink to understand the difference between what happens when that water is moving smoothly and what happens when it's moving chaotically. So these are things we're interested in understanding. So we need new tools to understand them. We just can't apply the tools of Newtonian physics to them. Another thing we're really interested in predicting is the weather. Okay? Here is a, and I showed this last time, tropical storm Isaac from way back in, I think, 2011 or 2010, 2011. And you see this when hurricane season comes along. They'll plot these tracks of hurricanes. But you see how unspecific the tracks of the hurricanes are. There's our best guess, which is kind of this red line up the middle, but there's this huge, what the weather forecaster sometimes calls the cone of uncertainty. Okay? In other words, it might hit right in New Orleans, but it might hit near Pensacola, and it might hit near Mobile, Alabama, or it might hit all the way over in Mississippi. We're not sure. Why aren't we sure? We're not sure because we don't have enough information to know exactly where every air molecule off the coast of Cuba is moving and how fast, and exactly what the temperature is at every square cubic centimeter of air that makes up the atmosphere. And even if we did, making the prediction of exactly what that air is going to do in a minute, an hour, 12 hours, 3 days, is very, very difficult. Okay? The equations are complicated. The amount of information is large, and the equations exhibit what we call sensitive dependence. In other words, if you make the tiniest change in what the air is doing here, that can magnify itself into a very big change. So the sensitive dependence, the fact that complex systems exhibit much more sensitivity than Newtonian systems, is the reason we have this thing called chaos theory. Lorentz in the 1960s coined this term, the butterfly effect, to describe this. And the metaphor he gave was that a butterfly flapping its wings in Brazil can change whether there's a clear day or a cloudy day in, let's say, East Hampton. He didn't use East Hampton, but let's say East Hampton a week later. In other words, the weather today depends on the weather yesterday, which depends on motion of air hundreds, thousands of miles away. And tiny changes in those initial conditions can magnify themselves and snowball into much, much bigger effects. So a flap of a butterfly's wing could change the situation from a clear day to a tornado a week later, depending on how those air molecules were moving. So our hope to predict exactly what's going to happen in any given situation is somewhat shattered by this. Now, why is this a problem? Okay. It's a problem because typically the way science has proceeded since the time of Newton to understanding how things work is by breaking them down into smaller and smaller and smaller pieces. And the way I understand what's going on this level is to break it down into something smaller. Suppose I wanted to understand why people behave the way they behave. Well, I would probably start by studying their brain. Okay? And I would poke around in their brain for a few years until I realized that the brain, what's going on in there, is there's neurons that make up the brain. And so I would start studying those, because you're going to understand what the brain does, you need to understand what the neurons do. So you start studying the biological properties of neurons. What do they do when you put an electrical current on them? How are they connected to their neighbors? What's the electrochemical nonsense that goes on in the synapse? I'm not a biologist. I don't understand any of that stuff. But I know that's what biologists are interested in. In order to understand what a neuron does, you need to understand all that stuff. You know, what are the neurotransmitters? What chemicals make up a neuron? How does the myelin sheath control the conductivity of the axon and nonsense? And so you need to understand some biochemistry in order to do that. In order to understand a cell, you need to understand the biochemicals that the cell is made out of. Well, in order to understand how serotonin is a different atom from dopamine, you need to understand chemistry. Okay? How are they structured differently? What atoms are they made out of? Why do they behave differently from one another? So to understand a neuron, you have to understand biochemistry, you have to understand chemistry, and to understand chemistry, why one atom bonds in a different way with the atom next to it, you have to understand physics, okay? Because after all chemistry is different amounts of electrical attraction between one atom and its neighbor. This process of viewing the key to understanding a system being understanding the parts of that system is sometimes called reductionism, okay? In other words, our understanding of the whole comes from understanding the parts. And we break it down into its parts. And we have this idea that if we understand what the parts are doing, all we have to do is kind of generalize up, and then we understand what the whole thing is doing. Okay? So I, as a theoretical particle physicist who studies quarks and neutrinos and electrons, am all the way down, okay, on this end of the diagram, the most reductionist of scientists that you can possibly be. Which makes me kind of a strange person to be giving the talk that I'm giving today. Because the fact that in reality, you really can't do that most of the time. In other words, once you break down the system into its parts, what you have lost is the explanation of the big picture you were trying to get at. And so what I want to talk about a little bit today, and what Bill Thompson was talking about earlier, is the possibility of flipping this diagram around and looking at how the interesting properties of things actually come when you go from the small scale to the bigger scale and look at these transitions from one kind of thing to another. In other words, what we're really interested in when we're studying quantum chemistry is how simple physics becomes chemistry. What we're really interested in when we're asking about neurons is how a bunch of neurons lead to consciousness. What we're really interested in is these jumps from one kind of phenomenon to another. Not taking everything apart and figuring out how the parts work, but understanding how the parts working together make something new. The original title of the 12th grade course at Ross School was Cosmos, Life, Brain, and Mind. And that course title was meant to illustrate the fact that what we're interested in as we kind of go back and look at the history of the universe all over again are these moments where something interesting happens, where you go from having just matter, just kind of being there and making rocks and stuff, to life, having something that is reproducing and evolving and changing over time. What happens when we have simple molecules to having a brain which responds to its environment and which reacts in a way that we regard as well, interesting, because we have one. And finally, how we go from having just a brain, like the brain of a worm or something that just kind of knows which direction up is and where to find the food, to a brain that has consciousness the way we think of consciousness, which we regard, because we're us, as somehow different or special or more than or qualitatively other than the consciousness of animals. So it's these transition points that we're really interested in. And it's the transition points that you miss when you do science reductively. In other words, if all I do is break down a brain into a big pile of neurons, I've missed the interesting thing that happens when those neurons get together and make consciousness. I've skipped right over it. It's not to say I won't learn interesting things, but I'll never really understand the thing I'm interested in, which is where consciousness comes from. Okay, the example I often give to my students is this. Imagine you're a city planner, and you want to understand why there's traffic jams. Here's my downtown during rush hour. It's a mess, right? Everybody's sitting in traffic. I want to understand why. Why are there traffic jams? If I took the reductionist approach to understanding why traffic jams happen in my city, I would wind up at the end of it looking at brake fluid under a microscope, right? Because that's ultimately the cause of traffic jams, right? Why do cars stop? Cars stop because people step on their brakes. Why does the car step? Because when people step on their brakes, because it compresses the brake fluid in the cylinder, and that presses the brake shoe against the car, and the car stops, okay? Is brake fluid the ultimate cause of traffic jams? Yes, absolutely. Have I learned anything particularly interesting or useful from that knowledge? Not really, right? In other words, how do I get rid of the traffic jams? Take away all the brake fluid, then you just got pile-ups instead, right? That's not going to help. What causes a traffic jam? What causes a traffic jam is a very complex relationship and set of rules that has to do with how one driver responds to a neighboring driver. In other words, the driver in front of me steps on their brakes, I step on my brakes. But the amount of distance that I leave between me and the car in front of me, and how hard I step on my brakes when I see that brake light, and how long of a time my reaction time is, those things are what really cause traffic jams. And you don't get the traffic jam until you have 10, 100, 1,000 cars all doing that thing at the same time. In other words, a traffic jam is something that emerges from the interactions of hundreds of drivers all following a particular rule. So the interesting thing it would be to figure out is not what the brake fluid is doing, but what the interaction is, what the rule is that determines how I react to the driver in front of me. And really what causes traffic jams is that most people drive like idiots and they think only of themselves, okay? I was driving home from the city a couple of days ago, and there was a backup on the Bell, the Bell Parkway, and I was trying my best to fight against the natural instincts of drivers, which is when the car in front of you takes off, you take off as fast as you can, you stay right behind them, okay? Because you don't want to lag behind, right? I want to get where I'm going as fast as possible. But what happens when you get as close to them as you can is the second they press on their brake a little bit, you've got to press on your brake a lot because you're not sure if you're going to hit them or not. And if you press on your brake a lot, the person behind you presses, and everybody stops again. If everybody just waited just 4 seconds, okay? 1, 2, 3, 4, and accelerated slowly and left that little gap between you. When this car tapped on its brakes, you wouldn't have to tap on your brakes yet. And that car might take off again, and you didn't have to slow down at all. Okay? If we all change the rule that we're using, that determines how we interact with our neighbors, traffic jams will go away. Okay? Well, not completely, but they won't persist in the way they persist according to current rules. So a lot of the behavior of individual drivers is the real cause of something like a traffic jam. But you can only understand that by going upwards from the reaction of a single driver rather than going downwards. So this idea of emergence is that rather than taking things apart and decomposing them into their pieces, we should look at the interactions between things and see what happens when those interactions go from being 10 things interacting to 100 things to 1,000 things. And what we've learned from doing this over the past 40 years or so, let's say, is that some really interesting things can happen when you have very simple rules being followed by lots and lots and lots of individuals. Right? We look at ants, we see them, following a line. I've got them in my house now that the seasons have changed. They follow a straight line from the door all the way to the crumb of, a cupcake that somebody left on the floor, and then back to their little ant homes. And you ask yourself, how do they do that? How do they know to walk in a straight line? Who's in charge? Who's the head ant who says, come on, guys, there's a cupcake over here, follow me? And they all walk in a straight line. Okay? That's not how ants work. There's no head ant. Okay? There's no coordination, there's no plan, nobody drew a map. And yet, this complex social emergent behavior, this behavior that's, and Bill used this word as well, self-organized. It comes from the interactions of the group, not from any one individual doing the organization. Just happens. If you look at a flock of birds, and if you've ever watched a flock of birds and watched the whole flock seemingly change direction all at once, it's like the whole thing has sort of a mind of its own, despite the fact that there's no one bird going, all right, birds, ready, 1, 2, 3, turn, right? Same thing with a school of fish. A school of fish almost looks, sometimes if they're packed closely enough together, like a single entity swimming around in the water. And it can turn on a dime, and all the fish look like they turn at once. Where does that behavior come from? If I start looking for the lead fish, I'll never find the origin of that behavior. What I can instead do is ask how the interactions between each fish and its neighbor could lead to this kind of complexity. Okay? One of the tools that we have today for looking at complex behavior that we didn't have in the 1960s is computer simulation. Okay? we can now on a computer, rather than trying to run a law like Newton's laws and compute it with math, we can just set up a physical system and let that physical system run according to the rules that we think are right and see if it gives the behavior that we're interested in. This is a simulation of turbulent fluid flow on a computer. Okay, the computer is simulating the motions of billions of atoms, or at least billions of locations, and the pressure and speed of the fluid in that location to produce something that looks like a pretty realistic sort of jet engine blast. This is a simulation of a tornado. Okay, if we're interested in understanding what causes tornadoes and how to have early warning systems of tornadoes, one way to understand them is to make fake tornadoes in the computer and see how they behave. The top right picture is an image from Big Brain, which is an attempt by IBM to understand how the brain works by just making a brain in the computer. In other words, instead of looking at MRIs of people and instead of poking wires in people's head, just make a bunch of neurons in the computer and connect them all to each other and just let it run and see what it does. See if it does something brainy. Rather than trying to figure out how brains work, let's just build a fake brain and see if it does what brains do. Maybe a little scary, but so far it's still in a box and we don't have to worry about it. The top left picture is actually a simulation of the universe from the point of the Big Bang 12 billion years into the future. That was just in the news this week. If you go check whatever your favorite news site is and Google universe simulation, and you'll come up with this story, and there's some beautiful videos and pictures. Rather than trying to sort of look at the universe with telescopes and figure out what stuff did, these cosmologists said, well, let's just put a bunch of hydrogen gas in the computer, run the simulation, and see if it does something that looks like what our universe did. And it actually really does really well. The quality of the simulation is really, really interesting. So the fact that we can now try to understand systems by just replaying the system 100 times, 1,000,000 times in the computer, change the rules a little bit every time, is something that scientists didn't have the ability to do, say, 40 years ago. Here's an example if we want to study the flocking birds. You guys all have NetLogo on your computers. So this is a simulation of birds. And they fly around. And what the computer program does is it flies the birds around, but the birds have a little rule about what to do if they get too close to another bird. If they get too close to another bird, they just turn a certain amount. But if they get too far from another bird, they turn a certain amount in the other direction. It's a really, really simple rule. You could write it down in a single sentence. Okay? When I run the program, though, the behavior I get is that over time, because they're all following the same rule, and they're all turning a little bit away from their neighbors if they're too far and towards their neighbors, sorry, the other way, away from their neighbor if they're too close, towards their neighbor if they're too far, the world wraps around like an old school video game. So when it goes off the top, it comes back on the bottom. They wind up in flocks. And I can set it up again with a different starting configuration of birds. And they wind up flocking up again. And sometimes the little pieces of flock will break off and they'll join again, kind of like real flocks of birds, if you've ever sat and watched a real flock of birds. Now, does this tell us exactly what's going on inside a bird's head? No. But it gives us a plausible model for what's going on inside a bird's head, and we can tweak it. In other words, we can set this angle. How much does it turn when it's close to another one? How far does it see? In other words, how close of a bird does it try to match its direction to? If I made this really small, they probably would take them a really long time to flock because they're not paying very good attention to the other birds around them. Yeah, these birds are a mess, right? But if I turn their vision up so they're paying closer attention to the birds in their vicinity, they actually flock up very, very nicely. So it lets us create a model of what might be going on to compare to reality. Okay? What's the alternative? Is sticking a bird in a laboratory and poking wires in its head and trying to figure out how bird brains work. Okay? Probably not as successful. We can do the same thing with ants. Okay? Here's a simulation. I set it up. So there's a ant hill, the little red bugs are ants, and these are piles of food. And if I set the simulation going, what happens is the ants just kind of wander around aimlessly. They're not very smart. But when they find some food, they release a chemical. And when other ants smell that chemical, they try to follow the trail of the chemical. And what you see is that the ants very quickly wind up making a line back and forth between the food and the ant nest. And now they've eaten all the food, and now, oh no, there's still some food left. Oh, and then one found that food, and then another one, the one in the upper left. So now they're going to wander around until somebody finds that food. Oh, we found it. It releases its chemical, and very quickly that chemical trail becomes the thing that the ants follow back and forth to the nest. So again, it's a model for this behavior that without knowing exactly what's going on in ants provides us a possible solution to how ants manage to look coordinated despite the fact that they are, kind of dumb little bugs. This idea of emergence is a really important one, I think, for science. But there's a problem with it right now. If we ask, what did Newton really do? Okay, why is Newton's accomplishment so important? Yeah, he came up with some laws, and they were mathematical, and they let you predict things. But what Newton really did, and what I think as a physicist I think is the most kind of central thing to realize about Newton, is that he unified what once were thought to be different sorts of things. What happens to a ball when you drop it, and what happens to the moon as it goes around the Earth, and what happens to a comet when it goes around the sun, and what happens to stars in a galaxy, which he didn't even know about in 1687, are all the same thing. They're gravity and Newton's laws of motion, and gravity and Newton's laws of motion can explain all those things using the same set of rules. This idea of emergence, that looking at how a few things following simple rules, if you turn that into 100 or 1,000 or 1,000,000 or 1,000,000,000 things, you can get self-organization, you can get new behaviors that emerge from those simple rules. Is right now, there are people who look at ants, and there are people who mess with tornadoes, and then there are people who study neurons and traffic jams and computer simulations. What there isn't yet is a sort of Isaac Newton for emergence. In other words, there isn't someone who's come up with a set of universal principles that can be universally applied that'll let us talk about complex systems in a way that knowing something about ants gives us insight to neurons, which gives us insight to tornadoes, which gives us insight to traffic jams. The way that understanding how a ball behaves when you throw it gives us insight to how the moon goes around the Earth that Newton did. So this study, this, and I won't even call it, it's not exactly even a field yet. It's sort of a signpost to a new way of doing science that's been around for 40, 50 years. Hasn't yet produced the kind of universal laws like an object at rest will remain at rest. Every action has an equal and opposite reaction. It hasn't produced a second law of thermodynamics in reverse. Right? The second law of thermodynamics says if you leave stuff alone, it'll generally get more and more of a mess, more chaotic. Right? Heat spreads out, things fall apart, things decay. What we really need for this science of emergence is sort of the opposite of that. When you set up a system in a certain way with certain kinds of rules, and the rules have to have these kind of features, what can happen is organization from chaos into order. And that's what all of these things are. Okay? A tornado is organization from chaos into order. Your current consciousness, your waking consciousness, is an organization of neurons in an ordered state. If your neurons were in a chaotic state, you'd be having a seizure right now. That's bad. Okay? But your neurons are firing in a way that's ordered, that's maybe shares something similar with what the ants are doing in an anthill. And so this approach to science, okay, the approach of trying to figure out if there's a universality to self-organization, if there's a universal set of rules that we can apply to all these complex systems, is probably going to be a big task for science in the next 50 years, and hopefully will lead to some insights that will allow us to tackle some pretty interesting problems like the problem of consciousness, like the problem of predicting the weather, like the problem of understanding how life got started in the first place, how we went from having just kind of organic molecules that do some interesting organic chemistry to actual honest-to-goodness living things. That's something we do not understand at all how happened. Okay? But it is an example of self-organization. It's an example of a bunch of chemicals getting together and making some system that persists over time, the way a tornado is a system that persists over time.